Hey everyone, I hope all of you can hear me.
Yes.
Thank you. Hey everyone, thank you for coming to my talk. We will be looking at what Container Runtime Interface is and how we can make changes to the Container Runtime Interface and the container runtimes themselves while working with Kubernetes. So let me introduce myself. My name is Sriram Venkitesh. I live in India and I work at DigitalOcean. I've been contributing to Kubernetes from 2022 and I'm mostly active in the release team as well as Signal, where I work with kubelet and container runtimes. So this is our agenda for our talk today. We will look at how Kubernetes works with container runtimes, and we will look at how it was before Container Runtime Interface was introduced and how it is working today. After that, we will go into the demo part of the talk, which is we'll see how we can compile Kubernetes locally and run our own cluster with kind. And after that, we'll see how we can compile Container B, which is the container runtime that we'll be looking at today, and how we can build Container B locally, and how we can create a cluster which has the custom build of Container B that we build. And we will also see how we can make changes to the CRI API and make both Kubernetes and the container runtime work with these changes. And finally, at the end of the talk, I would like to talk a bit about Kubernetes enhancements proposal that I was working on. It is called Container StopSignal, and we are adding support for StopSignal in the Kubernetes API. So I want to give a quick overview of the work that is happening there. And all of the things that I'm talking about in this talk, I learned from working on this Kubernetes enhancement proposal. So the talk is for 40 minutes, so this will be roughly our plan. Will take 10 minutes to go through what Container Runtime and Container Runtime Interface is. Then we'll take another 10 minutes to see how we can build Kubernetes, and then we'll see how we build Container Runtime and run Kubernetes cluster with the custom Container Runtime. Then at the end we'll go over the demo. So Kubernetes, as you all know, orchestrates different containers, but the actual work of creating the container and running them on the machine is done by the container runtime. So all the heavy lifting of the container creation and container, the cleaning up the containers after they are deleted and all of that is done by the container runtime. And this is how it looks today. We have Kubernetes which is orchestrating everything, and in each worker node we have the kubelet that is running, and the kubelet will talk to the container runtime, and the container runtime will create the container in the machine. So when we tell Kubernetes to create a deployment, Kubernetes will create a deployment, and then the deployment will create the pod and all of that, and kubelet would once the pod is scheduled to the kubelet, kubelet passes all that information to the container runtime. And till this point, the container does not exist. It is just metadata being passed around by the different components of Kubernetes. And the container runtime is the actual place where the process gets created. So this was how it used to look like in the past. Kubernetes had a lot of logic that was hard-coded to Docker, because Kubernetes was initially started with Docker, and Docker internally uses Container B to create the containers. But sometime after Kubernetes started getting popular, people wanted to use different container runtimes with Kubernetes other than Docker. So what they come up with, and when I say they, I mean the Node special interest group, the maintainers decided to create something called the Container Runtime Interface. And the Container Runtime Interface lets you to run Kubernetes with different container runtimes without having to build Kubernetes again. So in the first picture, this is how it was earlier. So there was logic which was specific to Docker, hard-coded in the kubelet. So Kubernetes would only work with Docker. But now the design has been changed so that the kubelet defines a set of APIs called the Container Runtime Interface, and any container runtime that implements these APIs can work with Kubernetes. So this is how it looked after the CRI was implemented. So all the logic specific to Docker that was hard-coded in kubelet was extracted to a new component called Docker shim, and Docker shim was compliant with CRI. So it will understand the new container runtime interface APIs, and kubelet only has the APIs, and whatever container runtime is able to talk in this language will be able to work with Kubernetes. So today we have kubelet, and the kubelet has the CRI APIs, and any container runtime that implements the CRI API, we can plug it with Kubernetes and make Kubernetes run with that particular container runtime. So I tried to use a Claude to generate an image to show this better. Disclaimer: this image is generated by AI, and this is how it looked. So the kubelet had specific APIs which are specific to Docker, which are specific to how Docker would create containers, and Kubernetes would speak to Docker in such a way that it will pass the information required to create the container to Docker. And this is fixed, and because of this, we were only able to use the Docker runtime. But now we have the container runtime interface, which is like I am trying to show it as a piece of a puzzle here, to which different container runtimes can fit into. So all of these container runtimes, like Container D or Cryo, they all implement the CRI, and because they have the CRI API implementation, we can use any of the container runtimes with Kubernetes. So if you are interested in biochemistry, this is a good analogy to understand. We have different proteins, and they bind to different enzymes. So similarly, if you are drinking coffee, then the caffeine molecule would fix itself to the brain cells, and the adenosine molecule would not be able to, so you don't feel tired. So similarly, we have Kubernetes, and we can fit different container runtimes. So now, with all of that out of the way, we are going to see how all of this works. So before I go into the container runtime part, I want to show you how we can build Kubernetes locally. So what I am going to do here is I will clone Kubernetes repo, and then I also install kind. So kind is oops, I don't think I'm connected to Wi-Fi. So kind basically stands for Kubernetes in Docker, and kind is a project that is an alternative to Minikube. So you can use kind to run clusters in your machine locally. So I'll show how that works. Yeah, this is the website for the kind project. So you can run kind create cluster, and it will run a cluster. It will create a cluster in your laptop, which will be running inside Docker containers. So we will first create a cluster using kind, and what we will do is we will build. So this is how you can build a cluster with kind. So you can either just say kind create cluster and then pass a name, and it will create a cluster with the latest Kubernetes version, or you can write the configuration file and use that config file to create a cluster based on your settings. So how this is how a configuration file for kind would look like. So you can define the name of the cluster, and then you can define however many nodes you want. So so this is an example. Let me know if the font size is not big enough. So this is an example kind cluster config. So let's say you want a cluster with 3 nodes. So what you can do is you can copy paste this one, and now if you run kind create cluster and pass this config file, it will create a cluster in your machine which has 3 nodes, and these 3 nodes should be running as 3 different Docker containers. And you can define the image here. So it can be Kubernetes 132, or this latest is something else. I will come to that. But if you want a cluster where one node is running on Kubernetes 131 and another node is running on 132, you can come up with custom config files like this. So the point that I want to convey here is that kind is very powerful. It's a powerful tool, and you can do a lot of things with the config file, which I will go into. So I'm not going to run all of this right now because it might take time. The Kubernetes takes around 10-15 minutes to compile. So I will not do that, but I have the output in my terminal, so I can show you the commands and walk you through everything. So first I clone the Kubernetes repository. So once I did that, I am inside, this is the Kubernetes repo, and I have all the files. And this particular terminal, you can see I cd into the Kubernetes directory, which I have named Kubernetes KCD Taipei, and I run this command, kind build node image, and I also pass this argument called arm64. This is because I'm using a M1 MacBook. So for that particular architecture, I need to make sure that the Docker image that is being created is made for the ARM architecture. So otherwise I will not be able to run that container in my machine. So if you are using an Intel laptop, then you don't need to pass this. You just need to say kind build node image and then pass the directory, which is I'm inside the Kubernetes directory, so I pass the node. And this command would take some time, and it would build all the different components like the kubelet, kubectl, API server scheduler, and all of that. And once that is done, you can see this line that says image kindest node latest build completed. So this will create an image in your machine that, like, it will compile the Kubernetes source code, and you get the image, like you get the compiled Kubernetes source code as a Docker image in your machine. So if I do Docker images and get for kindest, so the name of the image was kindest node latest, and if I see if that image is present, I can see that kindest node latest is it was created 48 minutes ago. So I was setting that up before the talk. So we have that image, and whatever source code that we have for Kubernetes is compiled into an image. And now what I can do is I can create a cluster. So in this particular terminal, you can see my kind cluster config. So this is a cluster named KCD Taipei cluster, and the image is kindest node latest, which is the image that we just built now. And when I do kind create cluster and pass this config file, it says it shows a bunch of steps, and at the end it creates the cluster. So I can quickly show you. So if I do KEP nodes, I can see a cluster running, but this is a different one. Actually, I have 3 different clusters running on my laptop right now to show different parts of the demo. But this is how it would look like once kind creates the cluster. And if you open Docker dashboard, if you are using Docker to run these clusters, you can see this. Like there are different. You can see that there are different containers running, and you can see containers like KCD Taipei cluster control plane, and yeah, these are all the other clusters. And if like right now my cluster only has a single control plane node, because I have defined only one node in the configuration file. But if you have defined multiple nodes here, each node would come up as a new container here. So before I go into the rest of the talk, I know that I'm dumping a lot of information. Does anybody have any questions, or am I not clear enough? If anyone has any questions, I can take them now before going into the rest of the talk. Okay, yeah, thanks. Alright, so now what I will do is I have Kubernetes source code, and what I have done is inside the kubelet.go file. So this is the file where the kubelet is starting, and there is a function called new main kubelet. I hope the font size is big enough. So there is a function called new main kubelet, and inside of this I added a log line that says hello KCD Taipei. And now when we build this source code, when we start Kubernetes, if you look inside the logs, we should be able to see this line printed. So once I added this line, what I did is I built the kind image again, and then once the cluster was started, so this is the config file. Yeah, so that this is where I built the Kubernetes image itself using kind build node image, and once this is done, we get this kind as node latest image. And if I look at the changes using git status, I can see that the kubelet.co file is updated. And if I look at the change, I can see that we have added a new line that logs hello KCD Taipei. So once we have this build, since we have this image now, we use kind to create a cluster based on that new image. And once that cluster is running, what I will do is I will open my Docker dashboard, and if I go to the KCD Taipei cluster control plane, I can click on exec, and these yeah, I think I lost my history, but what I will show you is if I do journal ctl -u kubelet, we get a lot of logs from kubelet, but if I search for KCD, I can see a line here that says hello KCD Taipei. I hope that is readable. Yeah, I'm not sure if you can read this from the end of the room, but we have a log in the kubelet that says hello KCD Taipei, and at this point what I want to show you is the entire, I want to go through that entire flow again. This is how I use kind to build Kubernetes locally, and if I want to make a new change, for example, I added a new log here that says hello KCD Taipei, and after this I build I have some changes to Kubernetes locally, and I want to compile all of these changes, and I use kind build node image command to build the image, And the image that we get here, kindest not latest, this has the code that will print hello KCD Taipei. So when I use kind to create a cluster using this image, it will create a cluster, and inside that cluster, if I go and see, I can see the line is printed. So coming back to the slides, we can create clusters. We can pass a config file to the cluster, and we can build the Kubernetes source code using kind as well. And this is how my cluster config file looks like, and this image is the one that we built using kind build node image. And when I create a cluster based on this config file, it has the log line inside. So that is how we build Kubernetes. Now I want to go into how we can make changes to the container runtime and compile container runtime locally and use that container runtime to run Kubernetes. So I am going to use container D. So for container D, we can run make and to create the container D binary. And in my case, again, since I am running this from an environment MacBook, I need to pass the Go operating system as Linux and the architecture as ARM64. So let me show you how I've done that. So I am inside the container D directory, and I run this command make, and I pass the Go architecture as ARM64 and the Go operating system as Linux, and this will build all the container D binaries, and you can find them inside. So this is the container D repo I have opened. You can find the binaries inside the build directory. So once you run make inside container D, it will compile the container runtime and you will get binaries for container D and different of the CTR command line, all of that. But we are only dealing with container D here. So after this, what we need to do is we have our kindest node latest image. So this one has the change to the Kubernetes source code, but it does not know anything about our new container D binary. So I want to, what I want to do now is I added a log line that said hello KCD Taipei from kubelet. Now I want to do the same from inside the container runtime. So what we can do is we create a new Docker file, and the base image for this Docker file is the Kubernetes image that we built. So kindest node latest. And in this Docker file, we have a container. What we will do is this build/containerd file, the binary that we just compiled now. We will copy this inside the new container image that we are building. So we start with the Kubernetes image. We copy our custom container D inside user local bin container D, and then we change the permission so that it is executable, and we use this to build a new image. So that new image will have changes to both our Kubernetes source code as well as the container runtime. So that will look like this. So if you create this Docker file, and if you run docker build, I'm going to name this image as kindest node custom container D. So we start with the kindest node latest image, which has our changes to Kubernetes, and we run this command to compile container D, and then we copy that container D binary inside our. We create a new Docker image where we start with the Kubernetes image, and then we copy our custom container D binary inside that image. So now we can have, we will get a single image. So we get an image called kindest node custom container D, and this image will have both changes to the Kubernetes source code as well as the container runtime. And yeah, we can use this image to build a new cluster. So I have the container source code, and what I am doing here is there is a file called container start, and there is a function called start container. So this is the function that is called to actually create a container. So every time Kubernetes creates a new container, the kubelet will send that request to the container runtime through the CRI API, and you can see that here. So this start container function, and this detail is not necessary for this talk, but the start container function takes two arguments. It has a context and it has a runtime.start container request. And if you look at what this start container request is, it is something from inside the CRI API package. So this is how kubelet is talking to container B. And similarly, if you take any other container runtime, like CRI would also have a similar function which would use this runtime.start container request. So that is how they are linked. Like the kubelet has a common interface which it will pass to different container runtimes, and container runtimes would have to implement based on the CRI API whatever function they are doing. So we have start container function, and this will be run every time a container is created. So there is a lot of logic. I don't understand any of that. The only thing I do here is I added a new log line that said hello KCD Taipei from container B. And once I add this line, what I have done is I build container B again using the make command, and I get the binary, and I write this Docker file. Let me see here. Wrong folder. Yeah, I write this Docker file, and then from inside the container B directory, I build a new image called kindest node custom container B. And once this is done, we again have maybe we can ignore that. Yeah, this is how the image gets built, and what it does is it takes kindest node latest, and then it will copy our custom container binary inside, and it will replace the existing binary. So when we build Kubernetes, it comes with a basic like a default container B. We replace that with our own new container B, and then we get a new image called custom container B. And we can see here that kindest node custom container B. This was created after I run this command, and this is how the Docker file looks. And after this, what I did was I have a new cluster. I have a new cluster where the image is custom container. You can ignore this line that I have commented. I will come back to that at the end of the talk. But the only change here from our earlier cluster, which is this one, is that here the image was kindest node latest, and in this one we have a new image called kindest node custom container. And once we create a new image, once we create a new cluster based on this one, so we have, this is our configuration file where we have the custom container B. I create a new cluster called a custom container B cluster, and that cluster gets created. So if I see the custom container B cluster control plane, which is the Docker container that KEP is running on my machine. So if I come here and if I do journal ctl container B, I can see the logs of container B, and if I search for hello, I can see a log line that says hello KCD Taipei from container B. So again, here what we have done is we compile Kubernetes. So in this cluster, that change is also there. So if I search, if I do journal ctl kubelet, and if I search for KCD Taipei, so we can see that as well. So this custom container cluster has changes to both the kubelet as well as the container runtime. So that was what we saw earlier. So kubelet is there, and if we do journal ctl container D again, we can see that whatever changes that we had added to the container D source code, we are able to see it here. And interestingly, we can see that this is repeated many times, as you can see here. So if I scroll down, we can see that this particular log line is coming up a lot of times. The reason for this is because we edited the start container function. So every time the start container function is called, it will log this line. And when Kubernetes is starting, it has a list of containers that it will create. So if I do kubelet pods for all namespaces, I can see that we have a bunch of containers for the API server and the KCD and all of that. So each time this container is getting created, every single time the start container function is called, and for all of these containers, we are printing hello KCD Taipei from container. And if you want to play around with this more, you can do things like we can get the container name. So here, if you do container dot, you can get all of the information like the name or the image or the container ID or container config, and then the container config would have all the things that all the information that the Kubernetes API is sending. So you can get the environments or like environment variables or like the volume amount and things like that. So you can try printing each of those from inside this log line, and instead of just getting hello KCD Taipei from container D, you can print something like hello KCD Taipei from the Kube API server container and HCD container and so on. So right now this information is like kind of repetitive, and we don't know which start container call is triggering this log line, but we can play around with it and learn more. Yeah, so that is how you work with both Kubernetes and container runtimes, and how you can test your changes locally, both in Kubernetes and container runtimes, like container D. So this is the example for container D, but the process for CRI-O would also be the same. The only difference being you need to compile CRI-O based on their instructions, and in the Docker file that we created, we will be replacing the we will make Kubernetes work with CRI-O first, and then we replace that image with our custom image. So that is essentially the entire entirety of my talk. And as conclusion, I would like to share about a Kubernetes enhancement proposal I did. So I am not sure if you can read the text there. I can share the link to the slides. But I added a feature called container StopSignals. So right now, if you want to kill a container, you have an instruction called StopSignal, and you can define this in the container image. So if I search for proper StopSignal, so we have an instruction called StopSignal, with which you can define a signal that will be sent to the container when the container is terminated. So this would look something like this. So if you want Nginx, and the default StopSignal for Nginx would be seek term, and once the pod, when you kill the pod, kubelet would send a sig term. The kubelet would ask the container runtime to send a sig term signal to the container, and it would wait for the container to terminate. And if it goes beyond the maximum term, the grace period seconds, it will send a sig kill and forcefully kill the container. But if you have a container that has like custom logic that would react to all the different stop signals, like in this case, I am giving a user-defined signal one. So if I want to do that today, I have to build the Docker image again, and I have to use this new Docker image. But what we wanted to do was add a new lifecycle in the container spec of the Kubernetes API, where you can specify the signal directly from the YAML. So you don't need to build a new container image. So this is not possible. Actually, this is not like this was released in Kubernetes 134, and only the API changes are there right now. The container PE changes are still, the PR still has to be merged, but the changes to cryo runtime has been merged. So let me quickly show that. Yeah, if you open this enhancement proposal, there is an issue that is created for all Kubernetes enhancement proposal. You can find this in the Kubernetes/enhancements repository, and for each new feature we create an issue. That is how we track the progress. So this is released as alpha 133, and the kubelet has, the Kubernetes API has changes with which we allow this new field, and we have corresponding changes to the container runtime to actually take this stop signal and do the processing that is required to kill the container with that custom stop signal. So I quickly want to show how this would look like. So here I am running a container, I am running a Kubernetes cluster with 132. So this is the pod spec that I am trying to apply, and this pod spec has the container spec has the stop signal defined, and in a 132 cluster, so you can see here the version says 132. So when we try to apply this code, it says with bad request, pod in version v1 cannot be handled, unknown field, containers.lifecycle.stop signal. So this is in 132, but in the image that I have built right now, I do have an output where I create the pod and get the status. Yeah, this one. So here what I have done is I have built a new image, and once the cluster is running, I can apply the pod and it did not throw an error. So if I look at the output, I can see that we have a custom stop signal, and the status also has a custom stop signal that we can see here. Yeah, this one. So this stop signal will be used by container runtime to kill the container. Yeah, that is the end of my talk. If you have any questions about contributing to Kubernetes or any of these, please feel free to talk to me. I'll be happy to help you. Thanks for listening.
大家有什么问题吗？现在先开放一位。没有的话，那我们就用掌声谢谢 Surin 给我们的分享。